This is Bernard Paulson. I will now discuss the material in Chapter 6. In the previous two chapters, 4 and 5, we looked at simple chemical and biochemical reactions taking place in a beaker. We will now move a step closer to realistic biological situations where material flows into the system and leaves the system. This is shown in this diagram using the mitochondria. The mitochondria is an open system where things flow in, like pyruvate, ATP, and inorganic phosphate, and ATP and CO2 flow out. All biological systems are open and reach a steady state or a homeostatic state relative to their environment. If you close a system off, it'll go to equilibrium, which technically is death in biology. So open systems are foundational to simulation in biology. This lecture will go through a few key topics. First, we'll talk about the key concepts in the analysis of open systems. Then I will place our simplest reaction from Chapter 4 in an open system where the reactant flows in and the product can leave. And then I will do the same thing for the Michaelis-Menten reaction covered in Chapter 5, where the substrate flows in and the product leaves, while the enzyme stays confined to the system. And then we'll discuss the lessons learned. So first up are the key concepts in dealing with open systems. First, we have to define the system's boundary. This divides the world into what's inside the boundary and what is outside the boundary. Then we define fluxes that cross the boundary, the inputs and the outputs. Inside the boundary, we have the internal network of reactions taking place. These are typically hard to observe non-invasively. This means if you want to know the interior of a cell, you have to break it up and destroy it. A few methods, such as NMR, an increasing number of intracellular biosensors, can give us non-invasive measurements from the inside of a cell. Once we have inputs and outputs, we will go from network maps to dynamic models, and then we wish to compute the functional states of these models. And they, most importantly, are the steady states, which come from solving the steady state equations, and the dynamic states that characterize the transition from one steady state to the next. And of course, in this class, we simulate these. Here is a diagram of a system where I have drawn a system's boundary. So there is an inside and there is an outside. On the inside, there is an internal reaction network at work, and across the boundary flow the inputs and the outputs leave. The system's boundary can be physical, such as a cell wall, the membrane of the nucleus, the membrane of the mitochondria, and so forth. We can also draw on a network map a virtual boundary around a process of interest, such as the amino acid biosynthetic pathways. That becomes a conceptual system, whereas in the former case, we have a physical system. Very often, for a physical system, we can measure the inputs and the outputs while the internal reactions are typically hard to observe. The boundary of a cell can be hard, which means that the volume is a constant. This is when we have a cell wall, as in a bacteria or in a plant cell. Or it can be soft, where it's fluffy, and the volume can change with time, such as for a circulating red blood cell in the human body. These are the basic concepts of dealing with an open system. We will now illustrate these with the simplest possible example, which is the reversible reaction in an open setting. I have now drawn a dashed box around the reversible reaction between x1 and x2 that we dealt with in detail in chapter 4. Now I have an input, a boundary flux number 1, B1, and I have an efflux or an outflux, or an output, I should say, boundary flux B2, which describes how x2 leaves the system. B1, the input, is often forced on the system. We decide what it is, and in system science, it's often referred to as a forcing function. Cells, of course, can regulate their inputs. For simulation purposes, again, we often specify B1. The outputs, the fluxes out of the system, are normally a function of an internal state variable. In this case, we might think of x2 as leaving the system by passive diffusion, so the efflux B2 increases with the concentration of x2 inside the system. This will behave then like a first order elementary reaction. I can write the stoichiometric matrix for the system, where the columns are the four fluxes shown, and the rows are the two concentrations. Note that the stoichiometric matrix we had for this system in a closed setting in chapter 4 consisted just of column 2 and 3, and the columns for the boundary fluxes B1 and B2 were not there. In this case, we have two concentrations, M equal to 2, 4 fluxes, N equal to 4. The rank of this matrix is 2. Therefore, the dimension of the null space is 2, and the dimension of the left null space is 0. The dimension of the left null space gives the space of all the steady-state flux vectors that satisfy this matrix, and the left null space simply tells us how many dependent rows there are in a matrix, and in this case there is none. The null space for the equation s dot v equal to 0 will have two vectors in it, and they are shown here as row vectors and ordered the same way as the columns in the stoichiometric matrix. If I transpose that matrix at the bottom to get a 4 by 2 matrix, 4 rows and 2 columns, and if I multiply S from the right with it, I will get 0. These two vectors in the null space are shown pictorially to the bottom right. The first one is comprised of boundary flux 1, internal flux 1, and boundary flux 2. In a steady state, all these have to be equal, since there is unity in the corresponding positions in the pathway vector in the null space. And this pictorially thus is simply a pathway through the system. It is an input, internal flux, and an output. The second vector shown is a cyclic internal pathway that corresponds to the equilibrium state of the reaction, something we saw in chapter 4. Now, here are the dynamic mass balances, which are the same as those we had in chapter 4, except I have a boundary flux coming in, creating x1, and a boundary flux leaving draining X2. At the steady state, these derivatives are equal. Based on that, I can calculate the steady state. I will begin with the flux vector. The flux vector in a steady state can be evaluated by simply substituting in the steady state concentrations into the elementary rate laws and populating that vector. I will solve for x1 and x2 steady state on the next slide. I know that the structure of the flux steady state solution will be a linear combination of the two basis vectors I had in the earlier slide. And these two basis vectors will have a weight A and B in front of them that are used to add them up to give me the actual steady state. I will solve for A and B in a moment. To solve for the steady state concentrations, I put the time derivatives to 0. I populate the right-hand sides with the elementary reaction rates, and I put it equal to 0, which in this case turns out to be two linear equations in two variables that are easily solved, and the solution is given towards the top of the slide. Note that both concentrations are proportional to B1, and we'll see this through simulations later on. I can now substitute these steady state values into the flux vector and separate it into the two basis vectors to get how the solution is spanned by the two basis vectors in the null space. Now I know that the coefficient A from the previous slide is B1, and the coefficient B is that group of numbers in the parentheses in front of the cyclic pathway. We see that the relative flux of the through pathway and the cyclic pathway differ by the ratio of K minus 1 to K2. This becomes important. We can now derive the mass action ratio and divide it by the equilibrium constant. This is shown in this slide. We have the mass action ratio as defined as the ratio between x2 and x1 in the steady state, and K equilibrium is the corresponding ratio in the equilibrium state. We have expressions for all these concentrations available, and we can substitute them in here and arrive at the fraction that is shown below. If K2 is much smaller than K1, that means that the efflux rate of X2 is much smaller than the return rate in the internal reaction, then this ratio will approach unity, which means the steady state concentrations become similar to those of the equilibrium concentrations, and therefore the steady state is close to an equilibrium state. Note that K2 divided by K minus 1 is a positive quantity, and therefore this ratio is slightly less than unity. And if it's less than unity, the reaction proceeds in the forward direction. That's a little characterization of the steady state solution. We can now perform the simulation of the dynamic mass balances. And the first thing I will do is to simulate this system for a set of numerical values shown in here. I'm going to put K1 to 1, K minus 1 to 2, as we did in chapter 4. And I'm going to put K2 to 0.01 and the boundary flux to 0.01. I have deliberately chosen K2 to be much smaller than K minus 1. In the workbook that comes with this chapter, you can change these values and resimulate if you like. I'm going to repeat the simulation we did in chapter 4 and start with x1 being 1 and x2 being 0. And then I simulate the response, and what I see is a rapid motion towards the equilibrium line, which is the line that has a slope of half as before. The line is not quite reached, and the curve bends and turns towards that line and drifts down towards it to the eventual steady state. And the steady state is achieved when t goes to infinity. In the steady state, the ratio between x2 and x1 is close to a half, but will actually be slightly less. x2 has to go to a value such that the product of it times k2, which is the exit rate, has to equal the input rate b1. So you can see if you multiply together x2 of 0.01 in the steady state times k2 of 0.1, you will get an efflux b2 that is equal to 0.01. That is exactly the same as the boundary flux entering. So the flux through pathway 1, the through pathway, will be 0.01. I can transform the concentrations into pools. Before I do that, let me return to this slide and discuss insert B briefly. Insert B shows x1 starting at 1, dropping very fast, and x2 rising very fast, and this is on this time scale of unity, just like the response was in chapter 4. In this case, that initial motion that lands the ratio of x2 to x1 close to a half is followed by a slow decay. And this is, of course, drainage of x1 and x2 from the system through boundary flux 2 to reach the steady state. Let me now transform the concentrations of x1 and x2 into the pools that I introduced in chapter 4. And that is done by simply multiplying the concentrations by the pooling matrix. And in this case, we get the disequilibrium variable and what was a conservation variable before. It'll now no longer be conserved, as the left null space has no dimension and there is no conserved pool in here. In this figure, I plot the phase plane of P2 versus P1, and then I have a little inset there with the transient responses of the two pools. In the beginning, x1 is 1 and x2 is 0, so I will start the simulation here at 1, 1. Initially, I see a rapid change in P1, which is the disequilibrium pool, towards 0. It's a vertical drop, which comes with a very small change in P2, that is the pool of x1 plus x2. This is followed by a motion along the x-axis in the horizontal direction, where the reaction is in a quasi-equilibrium state, and you see a slow drop in P1, which is the total mass in the system. It does not stay at 1, as it did for the closed system in chapter 4, but slowly drifts down towards a value of 0.3. The first pool, the disequilibrium pool, does not hit the x-axis. It doesn't go completely to 0, but very close to it. This means that the quasi-equilibrium state is away from the equilibrium state itself, and this is reflected by a slight positive value for the disequilibrium variable. The reaction in a steady state is not at equilibrium, but at a slight disequilibrium. Now, this simulation is completely meaningless from a biological standpoint because I cannot simply have the concentration of x2 be 0 and x1 be 1. The realistic simulations of open systems involve changes in the boundary flux. So what I'm going to do now is going to start this system out in the steady state achieved in the previous simulation, which is steady. It's a steady state. And I'm going to introduce a step change in the boundary flux going in the forcing function at time 0. I'm going to double it and then simulate. And in the panel to the left, I show the dynamic responses of P1 and P2. And you see the inventory goes from 0.3 to 0.6. It doubles as predicted by what I pointed out earlier, that both the concentrations in the steady state are proportional to B1 that I'm doubling here. And then you see the equilibrium pool increase slightly over time, very rapidly and slightly going up. The phase plane now of P1 and P2 involves a rapid vertical motion from the starting point, where P1 increases, goes to a slightly higher disequilibrium state, and then the inventory, P2, starts drifting from 0.3 to a higher value. You see that the P1 now is, you see it's a small number as shown with the scale on the x-axis. We have a relatively small change in P1, it's still a small number, and a larger change in the total inventory. Realistic perturbations are in the boundary conditions. This is simply like more of a nutrient becoming available to a cell, X1. It just picks up more and metabolizes more, goes a little bit more further from equilibrium because it has more things to consume. And we'd like to point out that sudden changes in the internal concentration simply do not happen. Occasionally, you might be able, with a light-sensitive metabolite, to deplete it by applying an external light. Unfortunately, the audio recording failed on the last slide, so I am re-recording the last few slides of this lecture. This may have caused some discontinuity in the tempo of the lecture and the sound of the audio, so I apologize for that. The lessons we learn from looking at the reversible reaction in an open setting are a few, and let me speak to a few of them. First, we learn that the boundary fluxes, the exchange fluxes, are very important, and what their relative response times are to the internal fluxes is important to know. Open systems are in a steady state and respond to external stimuli. This is a stark contrast to closed systems, where you start out with some initial condition and you move towards equilibrium. For open systems, you start typically out at a steady state and you perturb some of the boundary fluxes. These fluxes relate to changes in environmental conditions. They may relate to changes in the demands that are placed on a network and so forth. We can typically not change concentrations inside the cell discontinuously. We cannot just rapidly reset the initial conditions. We cannot simply reset the concentration of an internal metabolite as an initial condition and do a realistic simulation. In very, very few cases, this is possible. And one such example is when you have a photolabile compound inside a cell, you can rapidly ablate it by applying light from the outside, but of course typically that is not possible. We also did learn that if the internal dynamics to a system are fast compared to the boundary fluxes, we may not need to know them in great detail. So many of the lessons relevant to open systems are illustrated by the previous example. It was, of course, a very simple one. What we will do now is to look at the same sort of situation, except with an enzyme catalyzed reaction. And in doing so, there are a couple of additional lessons that we will learn. So now we are going to look at the Michaelis-Menten mechanism operating in an open setting. This means that the enzyme is confined within a system's boundary and the substrate can flow in and the product can leave. For the substrate, we have the boundary flux B1 that is fixed and forced on the system. The substrate flows into the cell or into the system and is then catalytically converted to the product by the enzyme. We now write down the differential equations, which are the same as before, except the differential equation for the substrate has a boundary flux in it, and the differential equation for the product has a removal term for the product, P. And here we assume that to be a first order process with K3 being the rate constant that characterizes the removal of the product. At time 0, we fix the concentrations, and in this slide we have generically put sub-zeros on the different species, but of course that initial condition will need to be the steady state concentration if we are to simulate in situations that are relevant. Here is the stoichiometric matrix for this system, similar to the one we had before, except we have the first and last column appearing now. In this case, we have now 4 compounds as before, but 5 fluxes. So our stoichiometric matrix is 4 by 5. The rank, on the other hand, is 3. So this means that dimension of the null space is 5 minus 3 or 2. We have a 2-dimensional steady-state flux space, just as we had for the reversible reaction. Here we have a left null space that has a dimension to it. It is m minus r, or 4 minus 3 equal to 1. Thus, there is one conservation variable, and it will be the total amount of the enzyme, as it cannot leave the system nor enter it. So the enzyme is either free or complexed with the substrate. We can now go through mathematics that are very similar to those we just went through for the reversible reaction. First, we can evaluate the 2 steady-state flux vectors that span the null space and represent the actual flux vector as linear combination of those 2 pathway vectors, and that is shown in this slide. In the first set of equations on this slide, where A and B are non-negative constants used to add up these vectors. And these are a through pathway that is comprised of B1, V1, 0 on V minus 1, and then V2 and V3. The second pathway, vector 0, 1, 1, 0, 0, represents just V1 and V minus 1 and is an internal reaction that is going back and forth. In the steady state, we have a simple flux balance that is shown here. We can use this flux balance along with the steady state equations to derive the steady state concentrations of all the four compounds. And they are shown here by these algebraic expressions. This takes a little bit of time to work out, but it's not too difficult. And then we can substitute these values for the steady state concentrations into the steady state flux vector given on the top, and then rearrange it and discover that the coefficient A is equal to the boundary flux. The coefficient B is the boundary flux times K minus 1 over K2. Basically, the same structure of the steady state solution as we had in the previous example. So this is a similar situation as before, with a couple of notable differences. First, these equations are bilinear that give a certain characteristic, and second, the total amount of enzyme is constant and confined to the system. Here is a simulation similar to the last simulation we had for the reversible reaction. We start out with the system in a steady state where the boundary flux is 0.025 and the numerical values of the kinetic constants are given. Then at time 0, we instantaneously change the boundary flux to 0.04 and simulate the response. Panels B and C show the dynamic response of the substrate in panel C and the intermediate X in panel B. The phase portrait in the background shows a curved line or a curved trace which corresponds to the quasi-steady state equation that we saw in chapter 5 when we looked at the Michaels-Menten mechanism applying the quasi-steady state assumption. The dynamic response here is such that we start out at time 0 on that hyperbolic curve and we move up it until we stop where time goes to infinity. In this case, the binding step of the substrate to the enzyme, characterized by K1 and K minus 1, is relatively rapid compared to the removal of the product from the system, characterized by K3. I will note here that if you open up the workbook for this case and try to put B1 to 0.05 or above, you will not get a steady state because you exceed the Vmax of the enzyme. And that is the first important lesson here is that the system now has an internal capacity constraint that you can exceed and break the function of the system. So as we saw in chapter 5, the Vmax through the Michaels-Menten reaction is K2 times the total concentration of enzyme. So if B1, the boundary flux, is forced to exceed that value, then the input rate, the influx rate of substrate will always exceed that of its catalytic conversion to a product. The catalytic conversion cannot keep up with the influx, and the substrate concentration will build up forever. And I believe for the numerical values given in this case, B1 has to be less than 0.05. And that is the limitation basically on the release step of the mechanism. Now, for a real cell, of course, we would have a genome that can synthesize and degrade an enzyme in response to an external stimuli. So if a cell would be forced to use a pathway at a higher rate than permitted by the total amount of enzyme at time zero, the cell might respond by synthesizing more enzyme and responding to the boundary flux in such a way that it can actually process all the substrate that comes into the cell. In chapter 9, we will see how this process is simulated. So that brings us to the end of this lecture. It is an important one because we now begin to look at open systems that reach a steady state. And this, of course, corresponds to a homeostatic state of a living cell or a living organism. Closed systems, in contrast, have no material flowing in and out and are doomed to head towards equilibrium as time goes to infinity. So living systems are open and they continually exchange mass and energy with the environment. And in fact, how far the steady state is away from the equilibrium state is important, as we shall see in subsequent lectures. In some ways, that's a measure of the distance between life and death. The continual net throughput a living cell, the homeostatic state, is really an energy dissipative state. It takes a substrate and secretes a product that is of lower energetic value. The cell or the system harvests some of that differential, but also a fair amount of it has to be dissipated simply by the laws of thermodynamics. Timescale separation shows up here as in other examples, and we'll see increasingly more of this feature as we go to more complicated systems. In this case, the examples given emphasize the importance between the timescale of the exchange fluxes relative to the internal fluxes. If the internal fluxes are very rapid, they simply track the dynamics of the inputs and the outputs. I will note at this point that we are thinking here about a system with a physical boundary, but as we analyze the internal dynamics, we will see that there are often fast subsystems within a network that we can draw a virtual boundary around and watch how the insides of that system track the fluxes coming in and out of it. In chapter 2, we saw this when we introduced the pooling phenomena and the formation of aggregate variables when we looked at the first 3 steps of the glycolytic pathway. In the second example here, when we introduced the enzyme, we saw that cells actually have internal capacities that can't be exceeded if the cells are stressed too much by a boundary flux that is higher than they can process. This concept is important in recognizing that cells have indeed a finite capacity to process material that flows into them, be that metabolites or signaling molecules or something else. So this lecture brings us to the end of part 2 of this text. where we apply the simulation procedures to simple examples. Chapters 4 and 5 treated chemical reactions in a closed system, with chapter 5 covering enzyme catalysis. And the final chapter here, covered in this lecture, chapter 6, shows what happens when a system is opened up and material flows in and out continually. The concepts introduced in this chapter are very relevant to the construction of simulators for living cells. With that, we will now stop dealing with toy systems, and we will move into part 2 of the textbook, where we start looking at real biological phenomena, and that part is broken into 3 chapters. In the first one, we introduce how we get numerical values for the kinetic constants. In the second one, we look at some of the important features of the stoichiometric texture of biochemical reaction networks. And in the third and last chapter of part 2, we look at the effects of regulation that is overlaid on top of the natural mass action tendency of the stoichiometric scaffold that represents a biochemical reaction network. Thank you for your attention.